Alright, welcome to lesson 14, the dot product for MA 103. And this lesson may be one of the most important lessons all block because we're going to use the dot product in the next two lessons where we do parametric equations and vector equations of lines and planes. And then we'll also use it when we start doing matrix algebra. And so we'll jump right into the definition straight out of your textbook that says the dot product or scalar product of two n-dimensional vectors u and v, denoted u dot v, is given by u1 times v1 plus u2 times v2 plus un times vn. Or we could just write that it is the summation of ui times vi, where I starts at 1 through the nth term. Okay, and so you see down here these two terms, scalar product and dot product, are synonymous. I think you'll most often hear us call it the dot product, but the reason why you may hear a scalar product as well is because you take these two vectors, and when you do this operation, the end result is a scalar value. So we'll start out trying to highlight a example you may be familiar with, and that is calculating the total value of some change. So what I did was I emptied my pockets, and here's a picture of how much change I had in there. So if I asked you to tell me the total value, I think what you guys would do is you would look at how many of each coin do I have, and you know the associated value, and you'd add it all up together, right? And so that's exactly what we're going to do. I'm going to write down two vectors, a quantity vector and a value vector. So here we go. We've got our vector Q, where 3 represents the number of quarters, 2 is the number of dimes, 4 is the number of nickels, and then we've got 4 pennies as well. Right? And so we could also label these as the components in a vector, where this first entry, the number of quarters is Q1, dimes is Q2, nickels is Q3, and pennies would be Q4. And then we've got the value. And so remember that one definition of a vector is a n-dimensional ordered list, and so the order matters, right? And so this first term has to correspond to the number or the value of quarters. So this would be V1, the value of dimes be V2, the value of nickels is V3, and the value of pennies is V4. And so now I've labeled each component in every vector. It'd be very easy for me to substitute this into our formula or the definition at the top of the page. So I went ahead and wrote out our equation here, but now I'll substitute the values in with you. And so the first thing we're going to do is substitute our quantity of quarters. So we've got 3 times its value, 0.25, plus 2 dimes times its value, plus the 4 nickels, and our 4 pennies. And so when we add all of this up, we get a grand total of $1.19. So to highlight just one more time that we took two vectors and the end result was a scalar value. Okay, and so now what I'm going to do is I'm going to go ahead and throw up some examples from our textbook, and we'll walk through one or two more. And so we're just going to scroll down here. I'm going to leave the definition on the page so we can all see it and refer to it. And now we'll look at problem 2.3.2, part A. Okay, and so if we wanted to do this, we could come in here and we could label this first vector as vector A and the second vector as vector B. And if we wanted to, we could also label each component, right? And so in here I could write that this first term is A1, second term is A2, B1, and B2. So if we wanted to compute the dot product of A dot B, we know that that's just going to be equal to A1 times B1 plus A2 times B2. And now we just substitute our values in, and so doing that we would have 2 times negative 1 plus 1 times 2. And when we simplify this expression, we'd have negative 2 plus 2, which would equal 0. Right? So again, dot product of two vectors gives us a scalar result, a scalar value. So now what I'd encourage you to do is I'd encourage you to pause the video and go ahead and work out problem 2.3.3, question B. So we'll tackle this one next. And so if you pause the video and you did the dot product of of these two vectors, your work should look very similar to mine, where I found that the dot product of A and B was equal to 20. Alright, we're going to talk about this last problem as well. So problem 2.3.4, we ask you to compute the following dot product if possible, right? And so if we look at this and we label the two vectors as we've been doing, we would label the first vector as A and the second vector as B. And we may notice there's an issue right off the bat, right? And that's that the dimensions don't match. And so the dimensions for A, we would say that n is equal to 4. And the dimensions of B, we would say that n is equal to 3. And so up here at the top, where we talk about the scalar product of two n-dimensional vectors, they've got to be of the same dimension. And we simply can't perform the operation if the dimensions don't match. Okay, and so down here, for this problem, this is undefined. And we can't compute it. That's an important concept to remember, because when we get into performing matrix algebra, we're going to be taking the dot product of a row and a column, and if they aren't of the same length or the same dimension, then we cannot perform the operation. Alright, so the next topic that we're going to focus on here is understanding the magnitude of a vector. And so I've scrolled over here and we've got the definition of the magnitude pulled up. And this is straight out of the book. It just says that the length, magnitude, or the norm of any n-dimensional vector, u, which can be written as these vertical brackets of u, is the square root of u1 squared plus u2 squared plus u sub n squared, right? And so, or you could rewrite it as the square root of u dotted with itself. Okay, and so most often throughout the class, I think you're going to hear us refer to this as the magnitude, but it's also the same as the length of the vector. And so I've highlighted this example down here. We've got this vector 3, 4, right? And so if we want to figure out what is the length or the magnitude of a vector, how do we go about doing that? So we can think back to our days of geometry and right triangles. If we want to figure out the length of the hypotenuse, it would just be, a squared plus b squared is equal to c squared, right? And that's all we're doing here. And so to figure out the length of this, we're just going to say that the magnitude of vector u is equal to the square root of 3 squared plus 4 squared. And so that's the square root of 9 plus 16, or the square root of 25. And so we know that it's equal to 5, and that's the magnitude or the length of vector u. And so I could give you another vector, and I'll give you vector v in 3 dimensions, right? And so we'll say that v is equal to this vector 2, 6, and negative 4. And the same process follows for finding the length or the magnitude, right? And so if our goal is to find the magnitude of v, then we're just going to do the square root of the first term squared, so 2 squared plus 6 squared plus negative 4 squared, right? So we can simplify that. We say it's the square root of 4 plus 36 plus 16, and so that's going to be the square root of 56. That is the length or the magnitude of vector v. So that works for any dimension, any n dimensions of a vector. So now that we understand how to find the length or magnitude of a vector, the next topic that we will introduce is a unit vector. And so a unit vector is a vector that has a length of 1. Okay, and so we can take this vector v, the same vector that we just used. So let me scroll back up so we can see that. We can take this same vector v, and we know that it has a length of the square root of 56. But if we wanted to normalize that so that the vector had a length or overall magnitude of 1, then we can just scale that by taking the vector and dividing by its magnitude. Okay, and so what that would look like is the unit vector of v. And so we're going to say u be equal to our vector v, which was 2, 6, and negative 4. 2, 6, and negative 4 divided by the square root of 56. So we can't really divide vectors, but we can do scalar multiplication. We could rewrite this as 1 over the square root of 56 times 2, 6, and negative 4. We can just distribute that into the vector as well, and we could say it's 2 square root of 56, 2 over the square root of 56, 6 over the square root of 56, and negative 4 over the square root of 56. And so either of these two expressions would work. Those are both unit vectors of the vector v. And so if you wanted to check your work, you could just go back and calculate the magnitude of this vector, and it will equal 1. All right, and so we're going to introduce one final topic, and that's how the dot product relates to, we can relate the dot product to the angle between two vectors. And so this is a theorem straight out of the textbook, and it says the dot product of two n-dimensional vectors u and v, denoted u dot v, can be found taking the magnitude of u times the magnitude of v times cosine theta, where theta is the angle between the two vectors. And so I'm going to write up a quick example for us. Let's say we give you the magnitude of u is equal to 10, the magnitude of v is equal to the square root of 30, and theta, this angle of intersection, is equal to 45 degrees. Then we can figure out the dot product of u and v without ever knowing the vectors, just by saying u dot v is going to be equal to 10 times the square root of 30 times cosine of 45. And so we can simplify this expression, and we find that the dot product is equal to 38.7298. Right, and so dot product is a scalar value, and that's what we found. And so there we go. Now we can use this same equation maybe to solve for something more interesting, like what is the angle between two vectors that intersect. And so just by doing a little bit of algebra, we can rewrite this, right? And so let's see if I rewrite this equation. And so we could say u dot v is equal to the magnitude of u times the magnitude of v times cosine theta. And so if I give you two vectors, then we can figure out what the dot product is. We can figure out the magnitude of u, we can figure out the magnitude of v, and what we're looking for is what is this angle of intersection. And so I can just divide both sides by the magnitude of u times the magnitude of v, and so I would end up with u dot v over the magnitude of u times the magnitude of v is equal to cosine theta. Now if I want to solve for theta, I can do the arc cosine on both sides, and now what I have is theta is equal to the arc cosine of u dot v divided by the magnitude of u times the magnitude of v. So now I'm going to give us two new vectors. Okay, and so the first vector, u, will be equal to, we'll say it's 3, 4, and 9. And then v will be equal to negative 3, 9, and 1. Okay, and so we've got two vectors. We can figure out what the dot product is pretty easily, right? So u dot v is going to be equal to 3 times negative 3 plus 4 times 9 plus 9 times 1. So that gives us, let's see, 36, negative 9, and 9. So I apologize for going out of order there, but that equals 36, right? Okay, and so now we need the magnitude of u. So the magnitude of u should be equal to the square root of, let's see, 3 squared plus 4 squared plus 9 squared. So that's going to be the square root of 9 plus 16 plus 81. So that's the square root of 106. Now the magnitude of v would be equal to the square root of negative 3 squared plus 9 squared plus 1 squared, or the square root of 9 plus 81 plus 1. So that's going to be the square root of 91. Okay, so we've got those two things. Now we just got to figure out what is the angle of intersection. And so if I'm going to do that, first what I'm going to do is I'm going to slide down and give us a little bit more room to work. So we can slide down here. And we know that theta will be equal to this dot product. So 36 divided by, oops, let me leave some room here. We got to do the arc cosine, right? So cosine of 36 over the square root of 106 times the square root of 91. So we just put that in our calculator, but the thing you got to make sure is that when you put this expression into your calculator, make sure it says it's in degrees instead of radians. And if you do that, you should get an answer of 68.497 degrees. So now we've shown you how we can use this this definition, or rather this theorem, to solve for either the dot product of two vectors or to find the angle between two vectors. And so now we're going to touch on one last topic that's of interest to us, and that is to determine if two vectors are orthogonal. Because where we're going to go in the next two lessons is we're going to start talking about the vector equation of lines or the vector equation of planes. And sometimes we'll test to see if a point is on that line or on the plane. And if it's not, we want to find the shortest distance to get back to the line or to the plane. And the shortest distance will be one that's orthogonal. The most direct path or the direct route to the line or plane will always be orthogonal. And so if we just write back our base theorem on here again, we had something that looks like this. We had u dot v is equal to the magnitude of u times the magnitude of v times cosine theta. Right? And so if we want these two vectors to be intersecting at a 90-degree angle, then what is cosine theta, right? What is cosine of 90? Well, cosine of 90 is 0. And so that means this whole right-hand side, magnitude of u times the magnitude of v times 0, this whole right-hand side is going to equal 0. So that means that the dot product of u dot v is equal to 0 when the two vectors are orthogonal. So that's a very easy check, and it's one that you're going to see in the next two lessons. And so just to drive home this point, I'm going to give us two examples. And so the first, we'll take this vector negative 4, 3, and dot it with the vector 3, 2. We want to see if these two vectors are orthogonal. So when we compute the dot product, that's going to be negative 4 times 3 plus 3 times 2. So we've got negative 12 plus 6 is equal to negative 6. And I don't know what the angle of intersection is, but I know that it's not 90 degrees because the dot product was not equal to 0. Right? And so now let's look at one more example. And so now I'm going to give you guys this vector 1, 2, negative 6, dotted with the vector 1, 3, 1. And again, when we compute the dot product, we're going to have 1 times 1 plus 2 times 3 plus negative 6 times 1. And so when we simplify this, we've got 1 plus 6 minus 6 equals 1. And again, it's not equal to 0, so we know that this vector is not orthogonal. So I'm going to write up one last example. And so now we've got the same first vector, 1, 2, negative 6, dotted with this vector 2, 2, 1. So 2, 2, 1. And when we take the dot product here, we've got 1 times 2 plus 2 times 2 plus negative 6 times 1. And so we simplify that, we're going to get 2 plus 4 plus negative 6 which equals 0. And so we know that these two vectors right here are in fact orthogonal. And so now we've covered all the key concepts for lesson 14, and everyone should be ready to tackle class tomorrow.